All right, so we're back into video 2 now on fundamental theorem of line integrals. And in this video, we're focusing on how to find potential functions. So they give us this vector field f, and in this case, the vector field f is just two-dimensional, so it's just pq. And the p is 6xy plus y cubed, and the q is 3x squared plus 3xy squared plus e to the y. And so the test would be, is py equal to qx? That's how we would find out if it's conservative. And so let's try that. What is py? That looks like 6x plus 3y squared. And what is qx? 6x plus 3y squared plus 0. And those are in fact equal to each other. So it is conservative. Okay? Then they say find what function f, the potential function f, such that the gradient of f is equal to capital F. All right, so what we need here is grad f equal to vector field f. And that means that little fx should equal p, right? So if fx is equal to 6xy plus y cubed, then what do you think f is? Well, it's probably 3x squared y plus xy cubed plus a constant, I guess, right? And if that is f, then fx would equal to p. So now we want to know, is this correct? Well, let's try what is fy and see if that equals q. Because if fx is equal to p and fy is equal to q, then we found our f. And it could be any constant, actually. So what is fy? Well, fy for this conjectured f is 3x squared plus 3xy squared plus 0, and that is supposed to equal q, which is 3x squared plus 3xy squared plus e to the y. 3x squared plus 3xy squared plus e to the y. Oh, and so it almost matches up, right? It's just about matched here, except we've got trouble. And the trouble is with this constant. It turns out that constant isn't necessarily a constant. It could be a function of y. It's constant with respect to x. So that means our f really should have been 3x squared y plus xy cubed plus e to the y plus another constant. So now this is constant with respect to x, so if I take fx, I will get p, and if I take fy, I will get q, and then this d here really is just a number, some arbitrary constant. If this problem had an x and a y and a z in it, then you would have to repeat this one more step, because that d could be a function of z, so then you'd have to check that, but that's sort of the way this works. All right, and then we've got just a simple idea here, but it's important for the next theorem, and that's what's called types of regions. So not connected. So this is one region, but it's been split into two parts, so we say that region is not connected. This is one region. It is all connected with itself, but it has a hole in it right here. So we just say that that's a connected region. If the region doesn't have any holes in it and it's all in one piece, we say that's simply connected. And this is usually what we want. And in the next theorem, we're going to have a few things that require the region either to be connected or simply connected. And so that's what those words mean. You can have weird things happen if the region is not connected. And so that's sort of a technical number that we need for the next theorem. And the next theorem is the fundamental theorem of calculus. Well, I thought you already knew the fundamental theorem of calculus. That just says that If you want to know the area under a function, if you can find an antiderivative for that, then you can just evaluate it at the endpoints. Okay? And the key there is you've got some function, you've got the endpoints, and the area under that is equal to the antiderivative evaluated at the endpoint. So the key is that the antiderivative of f is capital F. Well, what we're going to do is we're just going to upgrade this to be, instead of a regular calculus integral, it's going to be a line integral, and instead of an antiderivative, it's going to be a potential function. But the other idea is exactly the same. You just evaluate the potential function at the endpoints. So hopefully that connects back to the fundamental theorem of calculus, the idea that the area under a curve, or the value of a line integral in some sense, can just be evaluated by its values, by the values of its antiderivative at the endpoints. And that's what the fundamental theorem of line integrals says. So let F be a continuous vector field on some open connected region. Okay, so it has to be connected. Okay, the word open isn't I mean, it's technically important, but it just means the region has an open boundary on it, like a circle, but that doesn't conclude its edge. Okay, so F has to be continuous on some open connected region. In R3, it works in R2 or R3. And you have some potential function F, so the gradient of that, the gradient of the little f is equal to the vector field. And then this is that line integral right here. So the value of that line integral is equal to the value of the potential function at b minus the value at a. And what's a and b? Well, if you've got the curve C, a is just the point where it starts, and b is the point where it stops. Okay? And this is true for all smooth-oriented curves from A to B contained in D. So this is true for any curve you can draw as long as that curve stays in that open connected region. That's what's important. Okay? So the point is the potential function acts in much the same way as an antiderivative does. It's just for line integrals. So that's pretty cool. Note it's this particular line integral. It's that circulation or that flow or that work line integral that we're talking about for this problem. All right, and then we'll do a little example. So consider the oriented curve C given parametrically by this vector here, vector function of time for t's between 0 and 1. How much work does the vector field F do in moving an object along C? Okay, so you've got some curve C, and you've got this vector field F. Who knows what it's doing, right? Maybe the wind is blowing or whatever model you're trying to talk about, and then you're on the curve and you're driving along, and the wind kind of blows you and you want to know the total work. Well, that would be a line integral of the vector field dotted with the tangent direction ds, right? And that's going to be, for the example written right here, a lot of work. But by the fundamental theorem of line integrals, that really should just be f of b minus f of a. F of b minus f of a, if I can find a potential function, right? If I can find that little f that's a potential function for vector field f, and a and b are the endpoints of the curve. So that's going to be a lot easier. I just have to find the potential function find the potential function for the vector field and find the endpoints for that curve. So let's see if we can do that. All right. So first, let me, well, now that we've kind of talked about the idea, let's see if we can make a little space here and work it out. So first, what is r of 0? Where did we start? We'll plug in 0. I get to 0 plus 0, comma 0 plus 0. Okay, so we started out at 0, 0. And what's r of 1? If I plug in 1, I'm going to get 1 cosine of pi. Cosine of pi is actually negative 1. Plus 1 sine of pi. Well, sine of pi is 0, so that's 0. And then sine of pi is 0. And then cosine of pi is -1, and that's 2 over 2. So I think 2 over 2 times -1. So I think I'm at just the point -1, -1. All right, so A is basically the point 0, 0, and B is the point -1, -1. And now I just need the potential function f. Okay, so let me erase this, and let's find the potential function f. So what is f? Okay, well, f should be a potential function for this vector field, but we already worked that out in the last problem. It was 3x squared y plus xy cubed plus e to the y, right? 3x squared y plus xy cubed plus e to the y. And technically, you could put plus 7 if you wanted to, but you just need any antiderivative or any potential function, and when you plug in that 7 minus 7, you just get 0. So I'm not going to put in plus 7, but one could. So then I just need to do f of -1, -1 minus f of 0, 0. And that will be the work done by the vector field for this problem. So that makes it a lot easier, and we can work that out if we want. We'd get, what, -3 plus 1 plus e to the -1 minus 0 plus 0 plus 1. So I think I would get, what, -3 plus e to the -1 as my work. And that's how you do an example problem where you use the fundamental theorem of line integrals to compute, right? So what is this equal to? It's this line integral for the work done, right? It's a line integral, which normally is a whole bunch of work to do, but we've simplified it because we found a potential function to just, now, of course, there's a little bit of work to finding that potential function, but it's just a regular old f of b minus f of a, which is a lot easier than sort of doing this line integral down here. So that's hopefully kind of the point of this that you want to take away from this problem. All right, and that's how you that's kind of how you do those kind of problems. So we'll see you in the next video for one more topic.